Dr. Subho,
Yes, sir.
I think we can start now because it's 3 o'clock. Slowly, people
Yeah.
will join.
Okay, sir. Okay.
So, first of all, very good afternoon to all of you. And myself, Professor N.P. Padhi, uh, Department of Electrical Engineering, IIT Roorkee, and currently serving as a director, MNIT Jaipur. We do have actually Dr. Subha Paul, who is currently working as an assistant professor at IIT BHU, and he has completed his PhD from IIT Roorkee. Today, what we will do in this live session, first of all, I'll request Dr. Subho to give a brief about the course and what is being expected out of this course, those who participate or take this course. And then we will open the floor to all of you to share some of your concerns. I will strongly recommend that your concerns to be written in the chat box, and then Dr. Subha will go through those chat box questions and then react accordingly so that there will be a harmony in the interaction session. Without wasting any time, once again, thank you all to be part of this our NPTEL course jointly run by myself and Dr. Subho. Now I'll hand it over to Dr. Subho. Dr. Subho, over to you.
Thank you, sir, for the introduction. And yeah, I will first ask IIT Roorkee e-learning center. Is it the recording has been started?
Yeah, yes, sir. It's going on.
Okay. Okay. Thank you. So first of all, I would like to thank all of you for joining this course on advanced distribution network analysis and operation. And we are just going to end this course maybe on 10th October. That is the last week we are running now. And you must have got the idea what we have covered in this course. But just for your clarity, I will try to summarize it a little bit. That we started with the introduction of the distribution network and how that is different from conventional transmission grid, and also your passive distribution network, what we have studied maybe in the undergraduate or maybe for the past 5 to 6 years time, where the network is only a not responding to the grid, it is just consuming the energy and not supplying energy back to the transmission network. But as slowly we are moving for the renewable energies, more and more adoption. So now it has become an active distribution network. So the introduction part was covered. After that, we started with the mathematical modeling of all those DERs and then the load flow studies. Then we covered the optimal power flow, both the deterministic, stochastic, and your multi-period OPF studies. Then we slowly moved for the reliability analysis, resiliency studies, transmission and distribution network interaction, which is a very crucial thing to carry out energy efficient operation of any distribution network. And then we followed by your ADMS, Advanced Distribution Management System. And to implement all of this, there is a backbone which is mostly neglected in all the power engineer studies. Wherever we'll do this OPF or wherever we'll do these resiliency studies, we just neglect the communication. But you all know that without communication, you cannot even do all these works. So that we have covered at our last module for the how the cyber physical networks and how the communication uh, quality of services can impact the operation of the distribution network. So that is the whole overview, you can say, the for this course. And now I would like to open this session for discussion. And if you have any question, you just write it down in the chat, and then I will be happy to answer it. Or you can just raise your hand that I will call your name and you can ask your question directly.
Yeah, that would be a good idea. They can raise their hand actually. Yeah.
Yeah. Yeah, so this is an open discussion. So you can just ask whatever you felt for this course, or if you want any extra knowledge from this course, this is just open for you to ask.
Hello, sir. Am
Yes.
I audible?
Yeah, yeah,
Hello.
you're audible. Yeah.
Sir, I have one query. Sir, in distribution network, we have non-linear loads. So I just want to ask how to deal with this non-linear load while doing the analysis of distribution system.
Yeah, very nice question. So, actually, you are right that mostly we are dealing with the linear loads whenever we go for any linear analysis of a distribution network. But you must have studied that voltage dependent loads, that as ZIP load model or your exponential load models. Those are mainly your nonlinear loads, which we normally deal, either we take it as an intact with the as a nonlinear model inside our OPF or load flow analysis. But solving those kind of model is quite difficult, because generally whenever we go with the nonlinear model, we have to take a quadratic equation or a cubic equation. So solving with this kind of problem is little bit difficult. So generally what we do first, we do it in a simplified manner, because the beauty of the distribution network is that from the substation node to the end node, if you go, then the voltage drops certainly, but as we are moving to the active distribution network, the voltage drop is not significant. So we take a very primitive assumption there that the voltages are close to the nominal voltage, and depending upon that, we take the as a simplification to make the model linearized, and that linear model we normally incorporate for the analysis for the OPF analysis or reliability analysis whatsoever. But there is a, obviously you will find some gap in the optimality of like what is expected from the nonlinear results that will not get for the linear results. But for the fast operation, we always don't go for the accuracy, we sometimes look for the fast solution. So this depends that which kind of problem you are addressing. If you are addressing for a planning problem, that means where the problem time, the solution time is not your concern, but the accuracy is the concern, because there you involved a huge amount of capital investment. So there obviously you can deal with the non-linear model, which is present with this voltage dependent loads, or you can take the angles as well with the load model. But and specifically for the power electronics load. But whenever you go for the, let's say, real time optimal power flow, or you are going for the TND interaction problem solution, at that time mostly we linearize with some assumptions that first of all that angles are very negligible, that means they are close to each other, so the difference between the angles between two buses are close to zero. So if that is zero, then angles are obviously the angle unbalancing effect or the nonlinearity effect will not be there, and the voltages will be considered to be close to the nominal voltage. Considering that, the linearization is done, and then it is accommodated for the real time analysis.
Okay, sir.
Yeah, we have a question in the chat box that uh, what types of data are typically available from a distribution network for ML applications? So I think you are talking about machine learning applications. So typically when we are dealing with the distribution network, first of all, we have to understand that the data received from the distribution grid is little bit different from the transmission grid. First of all, the transmission grids are quite observable. That means you have your SCADA system in place for a very good transmission network that is not present for the distribution grid. And you must have known about the schemes what now government of India is running. One of them is revamped distribution system scheme. The RDSS scheme says that we have to install more and more smart meters. So that is the first source of data capturing. That is a smart meter from where you will get the time depending upon your clock. If you want hourly data or minutes data or half hourly data or sometime daily data or seasonal variation, those kind of data are first captured. What is the behavioral pattern or the load pattern of the customers. That is the first consideration. Second, you can take the voltage data that you can get from your smart meter. If you go for a good quality smart meter, sometimes they give you the angle data as well, but that is not much implemented yet. Second is that micro PMUs, obviously phasor measurement units, which have been now is being deployed for your making like increasing the observability for the distribution grid. So generally, these two types of data we consider. That is, first is the power consumption, and second is the voltage and the angle. If this data are with you, then easily you can like estimate the network parameters, or you can estimate the network operations or whatsoever. Like for the machine learning applications, what is the applications you are looking for? Mostly we rely on these two or three types of data. And your second question is that what are the cyber security and data privacy issues in ML based smart grid? Actually, whenever we say that cybersecurity issues, first of all, that your RTUs or remote terminal units are mostly distributed in all over the network, right? So they are at the each and every nook and corner, and maybe from the substation or from the control centers, they are few kilometers away. So, and getting an Ethernet connection, direct Ethernet connection from that uh, unit or from RTU to your control center is a costly solution. So generally, other than having a dedicated communication network for the power system, what has been followed is that either the power grid, they share the normal communication topology or technology which is present in the city or in the village. They normally share that medium, and within that estimated bandwidth or that prescribed bandwidth, they share the data from that RTU to the communication or control center. So there is a very high chance when, because you don't have a dedicated platform, so there is a very high chance, because you know these mobile networks or internets, they are very prone or they are very open to the world. That means anyone can like just go come inside your network area or data area and can just take away your data and can mishandle it. So that is the first kind of cyber threat normally we see in case of a power system, which has been already been experienced in Ukraine in 2012, I guess, where the complete blackout has happened. Then is again we have I think last year we have witnessed it in Chile. So where actually this is called, you can say, like man in the middle attack, like when an hacker, he comes in between uh, your remote unit and the control center, and he just receives the data from the remote unit, modify it on its own, and then send that modified data to your control center. So if this kind of things are happen, then we call it a cyber attack. So making that uh, entire network cyber secure for the application, because we are going for machine learning applications, means you are transferring huge amount of data from your leaf end to your control center. So that is a very easy to just spoil that amount, that data. So just to avoid that, normally first thing is that encryption is done. Then that encryption code is only available with your control center. Other than that, no one can understand which kind of data is flowing. That is the first thing. Second thing is that you can also use, which is normally been followed now, that is called demodulation and modulation technique, where other than sending the data as an analog platform, you send the data as a digital platform, like an 1010 combination. And whenever you will send that 1010 combination and that has been reached, like there is only one chance that that can be hacked, that you can just topple 10 to 1, or you can make 1 to 0. Other than that, you cannot do anything. So that one change can deviate your binary. Like if you change that 0 to 1, that will change the complete decimal value deviated from the actual decimal value. So that has been easily been identified by the control center that something intrusion has been happened with this data. So generally, this kind of work or cybersecurity measures are generally been adopted by the distribution grid, or you can say power grid operators, to avoid the cyber threats. Okay, so I can see another. Yeah,
Good morning, sir.
yeah.
Sir, my question is how demand response can improve voltage stability in a distribution
Yeah,
system.
please continue. You are not audible. Can you please unmute yourself and okay.
Hello, sir. I have
So
written
yeah,
my
yeah, yeah.
question. How demand response can improve voltage stability in a distribution grid?
Okay. Actually, voltage stability, that means that you want your system or to run close to your nominal voltage, right? So we, and for the distribution network or power network, if you go from the main substation or from the generating plant, if you go further and further, that means you are just moving forward to the more and more electrical distance. That will cause your voltage drop, and that will reduce the voltage. That is quite obvious. So, and this power flow is because of your load. So generally in the demand response, whatever we see, that let's say you have a very peak demand, at that time, that means huge amount of current is flowing through your line, and that will cause a greater amount of losses, voltage losses in that line itself. So if that substation, your voltage is 1 per unit, let's say in the next bus that has been dropped to 0.99 per unit, and if you go to 5 or 10 or 20 buses apart, this has been reduced to 0.98. And then if you go to the leaf node, which is let's say 100 buses apart from your substation, this has reduced to let's say 0.91 or 0.89 or 0.88. So that is not permissible, because if you see the ANSI or IEEE or any kind of standards, then you will see that we have to keep our voltage within 0.95 per unit for distribution network. So there normally the distribution demand response comes into the picture. What demand response says, that you tell your customers to reduce the price or to reduce the load. That means you will give him some incentive, that if you reduce that load, you will get this much of rebate or this much of subsidy from your at your energy price. If that is the case, then at that time, then if the consumption has been reduced, then obviously the current flowing through that line will get reduced, and then the voltage drop will get reduced, and then that will enhance the leaf node voltage. Let's say previously it was 0.88, and now it has been increased to 0.92. Further, you have implemented demand response, then it has become 0.95. Then the stability of the network has been improved, because we know that in now, like running days, the loads are keep on increasing, because we are enhancing more and more electrical appliances in our homes, industries are coming. So if that is the case, then this, let's say now it is 0.88, and after 1 year down the line, this voltage will drop to 0.82. So that is not permissible. So if you go for actually network reinforcement or network upgradation, then you have to invest huge amount of capital cost to improve the voltage profile. And sometime maybe you have witnessed also in your home that some of the loads are very voltage critical node. So that's why we normally use stabilizer with the ACs to keep the AC fixed amount of voltage. And if it is not getting, then your AC will become damaged. So to avoid those situations, normally, and to avoid the huge amount of capital expenditure from the service provider's point of view, generally they are motivating the customers that you reduce your load at a certain point of time, at the peak load time. And then you will get some amount of incentives or subsidy from your service provider that will enhance the voltage of the network, and that will enhance the voltage stability.
Yes, sir.
Okay, so I can see one more question, that is, how does latency in communication channels affect closed loop stability of generator control systems in cyber physical grid? Okay, so actually the latency is generally present whenever, like, that creates the problem because we always want that data to be transferred from the customer side or from the node leaf end side to the control center or to the generating center within a snap, like within a microsecond time or let's say nanosecond time. But that is not the case. And generally the closed loop, the stability operations, they are very primary control operation, right? So they operate in millisecond and microsecond time. And if you see different mediums, let's say if you go with the PLC, which is not generally followed in India, power line communication, their latency is very high. Sometimes their latency goes to the millisecond time interval, or sometimes it goes to the second time interval. So if that is the case, so you want to run your closed loop control or your primary control in the microsecond time steps, and that needs the data. That means that needs that feedback, or you can say the input data from the tertiary control. That means the system definition or the system condition that has to be known to the primary control in each and every microsecond time if it is varying. But for the latency, if that is coming after few seconds, that means it has missed that chance, and then your closed loop control or your primary control cannot work properly. If that is the case, so at that time you will see these stability issues depending upon your voltage stability or your angle stability. But that is the main concern with this communication network, that latency, like the delay has not to be more than certain limits for each and every application. Like for generating or for this control center application, this has to be some milliseconds. If you go to the protection point of view, this has to be in the microsecond time interval. So depending upon the criticality, this latency varies. And if the latency is more, then obviously your system stability will be hampered in a huge manner. Okay. So the next question I can see from Vaibhav, that is, power distribution faces challenges from increasing AI driven power demands in data centers. How to handle it? Okay. So actually, the AI techniques are generally used in the power centers or the data centers to forecast the next time period or next day or maybe next year load demand. The problem with this AI driven techniques is that there is no AI technique which is a flawless. That means which can give you an 100% accurate result. So the problem comes with these data centers is that whenever your demand is less, let's say you are just forecasting for yourself, for a home, then this deviation can be a few kilowatts. So that will not create much problem. But if you add this for 1,000 or 2,000 or 10,000 customers, then 1 kilowatt will become your 10 megawatt. Now that creates problem, because if you have covered this course, you have might have seen that T&D interaction, where the distribution entity or the distribution service provider has to go to the market, that means the energy market, for the bidding, and that bidding will be cleared at the energy market, and if that is cleared, then it will come to your substation. But if your forecasting technique is not good enough, that means it is not capable to forecast with the, let's say, 99% accuracy, then, and if you have a, let's say, error of 5% or 10%, that error in the megawatt or gigawatt level will become very huge if you go to the actual unit. So when you are, let's say, bidding, let's say your load is actually 10 gigawatt, and now you are bidding for only 5 gigawatt because your AI technique has failed to predict it properly, then you are already shortage of that 5 gigawatt. So there is only two ways. Either you take that extra power from the market or from a generating station, paying paying more cost or penalty. That is the one option. Or second option, you just cut down that load from your distribution network. So both the ways, it is not favorable from the customer point of view, because if you purchase power from a costly solution or costly generating plants, that will be obviously that will be imposed on as a tariff on your customers, and you will try to recover that cost from your customers only. So that will come as a penalty to your customers who are not even like you guilty for that. You are only failed to predict the actual scenario. And if you just cut down, then that will seriously question the reliability or the trust of that service provider. So generally that actually faced by the power distribution companies. So and normally there's power distribution companies, they actually invest huge amount of money just to go for a good prediction of their loads. That may be a next day load, that may be a next year load, or that may be a seasonal variation. Because in our country, the loads are keep on varying and each and every month. Because now there's, let's say there's an October month, so there's a festive month. So this time load pattern is no way similar to the load pattern of September or let's say August. So each and every month and each and depending upon each and every season, this load patterns keeps on varying. And also the another challenges is the data, because generally our distribution networks in India or most of the countries are other than US or the European countries, most of the distribution networks are not much monitored. So that means your data, like when you want to predict something, you have to have the training data with you. So most of the cases, this training data is not even present with the distribution networks. So what they do normally, they take very synthetic data, or let's say you want to predict for UP and they are using the AI tool which has been developed by Gujarat. So the demography, complete the situation of the Gujarat and the UP is completely different. And if you are purchasing something which has been designed from or trained by the data from the Gujarat, and now you are trying to implement it for the UP, that is completely going to fail. So this kind of challenges actually normally the power distribution networks they face in using or adopting more and more AI techniques for real life application. Though it has now been encouraged, and with the SCADA system in the distribution networks or the PMU installation, they are trying to do it, but still we have to long way to go. Okay, so
Sir,
yeah,
sir, my question is, how does the inclusion of renewable energy sources affect the power flow equations and fault current levels?
okay. So actually, the renewable energies generally, whatever this distribution network we are using, like for the last few decades, we always think that this power will come from the substation, that is the transmission grid, and this will go to the customer end. So that is an unidirectional power flow. We always assume that it cannot be from the customer side to the substation side. But this scenario gets changed with the inclusion of the renewable energy sources, because now the government is also motivating and students like customers are also like installing more and more so rooftop solar panels. So at the daytime, these solar panels are generating power in the full capacity, and at that time mostly our consumption is quite less. So this power normally goes back to the grid. So the system which has been designed for unidirectional power flow, now it is experiencing a reverse power flow. So there comes the first problem with this protection algorithms, because generally whatever this relays are been deployed in the distribution grid, those are mainly your overcurrent relays. Overcurrent relays. So whenever they will, it will see that a reverse direction power is coming, and if it is not within the range, then it will fail to operate. That is the first problem. And the second problem is that as the renewable energies are coming inside, like in between the network, they are not integrated with the substation. So generally the relays are connected at the substation. So it can only measure the current, the fault current rather, I would say, which is flowing from the substation level. So if your fault current is coming from the substation and in the overcurrent relay is able to detect that fault current, then your system is good. But as our renewable energies are coming in between the substation and the customer or at the customer end, so at that time you don't have the relay operation. So if any fault occurs at the line and that is after your relay, so your renewable energy, if it is a solar panel or your battery, that will keeps on feeding the fault. So that is there. But your relay, which has been actually connected at the substation, it will see a very less amount of current flowing from that substation end. So we call it an overreach operation. So if that is the case, then your relay will not trip, and you don't have a good protection element, mostly in the customer side renewable energy sources, which can sense that fault and can trip. So that normally creates the problem with the protection point of view when you integrate more and more renewable energies in the distribution network.
Thank you so much, sir.
Okay, so I can see another question, which is like, what are the possible ways to mitigate voltage flickering in a distribution network? Okay, so the flickering can be avoided. First of all, you have to keep the keep the voltage stable. So that is normally been done by giving either your fax devices, you can keep like a capacitor bank, or you can keep a statcom. Now even if with the renewables, your inverters are also acting as a smart inverters, and they are also taking part for giving reactive power support or keeping the voltage constant at a particular bus. If those kinds of measures are generally taken to keep the voltage stable at a particular node, and if your voltage is stable, then you can avoid the flickers, other than if it is a manufacturing defect at the lighting side. Okay, so course, is there any distribution company is using graph based load flow? What are the pros and cons if ways of it is applied to the transmission network? Okay, so I will first answer the first question, that is the graph based load flow. So generally, if you see, not in India much that has been adopted, because as I have mentioned, that Indian distribution grid are not much monitored, and you must have seen for the graph based load flow that you have to create more matrix, right? So that means which node is connected with whom, and that will give you the path matrix. Then you have to calculate the load matrix. So there are so many matrix you have to calculate, and those are directly depends upon the network parameters. Okay, so but generally, if you go to the outside India, and there you will see that when your complete network structure is known to you, so at that time the graph based load flow has been used compared to your BIBC and BCVB load flow, that you have also seen. This graph based load flow are quite fast. And at considering your second question, there is a transmission network, there is a problem with the implementation of the graph based load flow for the transmission network, because generally whenever we use that graph based load flow, we want to avoid that sparsity present in the distribution grid. That is the problem with the when you implement a Newton-Raphson. But if you go to the graph based, then graph based method mainly says that you just take the data from your neighbors. So for a distribution network for a particular node, that there is only possibility of only two neighbors, two to maximum three neighbors. That means one parent, there cannot be more than one or two parents, and there cannot be more than one or two child. So if this level of sparsity is present, then creating those matrix for the graph based load flow is very easy. Now, in contrast with that, if you come to the transmission grid, there one bus can have multiple neighboring nodes, and that makes your each and every matrices in the graph based load flow become very huge. And doing that operation for transmission grid is difficult to do compared to your Newton-Raphson. Okay, so I can see another question, that is, how does the radial topology of distribution system influence the formulation and computational complexity of the OPF problem? Rather, I will say that the radial topology makes the solution process easier, because when you have an weakly meshed system, so at that time you cannot really estimate the power flow direction. Though from the radial also you can get the reverse power flow, but for the very highly meshed or weakly meshed network, the power direction can be from anywhere. That means if your one node is connected with 4 or 5 nodes, and then your power can come from any of the 4 nodes. But when you are radial topology, that makes the power direction or the voltage drop calculation very easier. What we have seen for that branch flow method, that you can easily use branch flow where you need not to deal with all those angles what we have dealt with the bus injection model. And that bus injection model is mostly favorable for this mesh network where you have to deal with the angle as well, because the power flow not only depends upon the voltage magnitude, that also depends upon the angle difference between the two nodes. And from there the power, I could say that the power flow from that bus will be very high. But for radial topology, if you see, if one bus is connected to only one parent node, that means there is no other option that it will either get power from that node, or it will share, or it will give a reverse power to that node. So the writing that voltage equation or writing the power flow equation becomes very easier to deal. So actually the formulation of radial topology is quite easier compared to your weakly mesh network or completely mesh distribution network. Any further question?
Hello, sir. Can you hear me?
Yeah.
Sir, how can we use the machine learning to improve the performance of distribution network?
Sorry, can you please repeat?
Sir, how can we use the machine learning to improve the performance of distribution system?
Okay. So actually, normally we use machine learning techniques because if you go with the classical models that we have discussed in our OPF or load graphical based load flow, the problem with the classical models is that you have to first know the entire network. This or network topology, or let's say the entire network mathematical model. So that is the first challenge, because if you go for a very smaller network, generally we don't use the machine learning. Let's say it is a 3 or 4 bus network. That is very easy to visualize and also very easy to mathematically model. So that we called as a white box model, where you know the entire topology or all the data from the small network. But let's say you go for a very huge network, let's say 8,500 bus network or 9,000 bus network or 10,000 bus network. It is very difficult to get the full idea of the entire node to network topology and as well as the data from each and every customer. So other than doing that, if you don't have the proper knowledge of the entire network, then you cannot go with these classical models like your branch flow model or your bus injection model or whatever the classical optimization or power flow models you have. You cannot go with that. So to avoid or to rescue from that situation, generally the machine learning techniques come where you will feed the data, whatever data you have in your hand. Obviously, because every month you have been billed, so your service provider or your utility have your monthly consumption data, or whatever how much like your SCADA system or PMUs are present in the network. From there, they have their voltage data, though it is not sufficient, but they have few amount of data. So that with that data they can train the machine learning uh, like models and can get a favorable decision. I should not say those are very optimal decisions, but those are favorable decisions for the network. So machine learning techniques are mostly good for when your system is becoming very large, and there generally the AI techniques have been used. Okay, I can see another question. Why is the OPF problem in distribution networks generally non-convex? And what network characteristics contribute to this non-convexity? Okay, so generally this operation is not the operation, but we could say the mathematical model is non-convex, because the relation between, as we have seen for the branch flow model or even the bus injection model, whenever we want to relate this voltage magnitude, voltage angle, power, active power flow, reactive power flow, and the current, these are your parameters in the entire network. So when you try to connect them, or to try to make a relation for them, that relation is coming out to be a non-linear, non-convex model. So that is coming out to be a cylindrical equation, like an equation we have seen, that p square plus q square equals to v into L. So that equation, whenever you will get a quadratic equality, that quadratic equality constraint is actually a non-convex. It is not like that your operation of the network has become non-convex, because that is mostly related with your mathematical terms. Whenever you are trying to simplify or you are trying to solve your network, you have to go with some mathematical models, or you have to represent the operation of the network as in a mathematical way. For doing that, when you are trying to establish the relationship between these parameters, that is coming out to be a non-convex or a non-linear equation. So dealing with this kind of non-convexity or non-linear equation in actually the in a coding or optimization level is difficult, because till now no solver has come in the market which can give you an unique solution or a good solution with the non-convex problem. So there actually the hindrance is that, because we don't have a particular solution algorithm which can solve that non-convex problem. If we can solve that, then that will be the biggest achievement for the power system. And then we need not to go with any kind of linearization technique or any kind of simplification technique. So though at the market ready operation is not present, so that is why we have to go with this extra simplifications. Anything else?
Sir,
Yeah.
sir, how can machine learning assist in congestion management in the distribution network with the EV charging clustering or related to that? I will
Machine
also post my question in chat box.
machine learning for EV charging. I could get your entire question. How can machine learning assist in congestion management in networks with electric vehicle charging clusters? Actually, the machine learning will not do congestion management. It will just it might be used for the demand response, because ultimately your EV charging stations or your EVs are coming as a load in the network. So those are your extra loads you are adding at the evening time or maybe at the noon time at the charging stations. So generally, we don't do congestion management for distribution network, because congestion management says that okay, you just whenever one line is overloaded, you just bypass that amount of power to the its parallel line or to the another path, to the longer path. But though in the distribution network, mostly those are radial strategy. So reaching to one particular node, you have only one option, only one path. You have no alternative path. So generally, we don't call it a congestion management operation. We call it a demand side management or demand response operation, where generally this machine learning techniques, they normally see, like, they are mostly used for two or three purposes. First purpose is that first to see how the EV growth is coming in the network, like your city or your village area, how much your customers are adopting EVs day by day. So that is the first concern. The second thing ML sees, that when the peak demand is coming, like evening time, at which time, 6 to 8 or 8 to 10 or 10 to 12, or at the midnight. Let's say it is a residential area, so everyone will start charging at the, let's say, 10 o'clock or 11 o'clock, from the morning till the morning, like 5 o'clock or 6 o'clock. So when this extra load is coming to your network, seeing the pattern of the EV charging, so there comes this ML, which will give you that pattern of that EV charging, that which time it is coming, how much it is coming, and also if it is charging station, for that it says that how many EVs can come for a particular time, And if it is coming, then your customers, this customers criticality level, like some customers will be of like they normally choose for fast charging, some customers they choose for slow charging. So this kind of segregations, this kind of, you can, so data handling strategies, or depending upon that what decision you will take, so those things normally decided by the AI. And apart from that, also one thing also currently it is coming, that your AI techniques normally also suggesting that depending upon the work pressure or the number of customers at your charging stations, or how many charging ports you have free at your charging stations, you will decide also the price. If one customer is becoming very critical and he wants his car to be charged at first, then obviously he has to pay more. So how much they has to pay more depending upon the situation of the charging station, and as well as depending upon the traffic condition of the city, that has also been now predicted by the AI techniques.
Thank you, sir.
Anyone else?
Sir, hello. Am I audible,
Yeah,
sir?
yeah.
Sir, I want to ask, how can we uh, place the DGs uh, or any PV in distribution network? Uh, is it required to place them optimally, or we can place them at any location?
Yeah, generally for this, if you see, there is two kinds of approaches has been adopted. One is, you could say, short term approach, one is long term approach. One, if you go with the long term approach, that says you go for the optimal planning, obviously. Like you are trying to plan it, let's say it is a big solar park of, let's say, 2 gigawatt capacity, that you cannot place anywhere in the network. That has to be located in a proper location that will not create overburden to your system, because generally we keep this RES in those positions where which will relieve the system stress. That means the under voltage condition or overloading condition, or maybe reduce the peak loads. Like we normally keep it at closer to the loading sections, not like, let's say, your loads are at one section and you have placed your renewable sources uh, to 10 kilometers or 20 kilometers away. So we lose that cheap energy while traveling to the network, like it will be lost as a network loss. So that those things are normally considered when you will go for the optimal planning, and that planning has to be from the 5 to 10 years time. If that is the case, then we go for that, for a large capacity renewable sources, or let's say wind farm or solar park. But whenever if you come to low level, let's say you want to just include, let's say one locality has to be electrified from the solar network just to reduce that load. So at that time, normally the utilities or the service providers, they normally point out the low voltage nodes where the voltage has been dimmed in a very significant manner at the peak load time. They just identify that node position, and there they install these solar panels. And at those point, customers are normally motivated or subsidized to include more and more renewable sources, until unless they are creating now the over voltage condition for your network. So that is also a problem with the renewable sources. If large penetration comes, so now no one is buying power, now everyone is trying to sell power. So if that is the case, so at that time the customer end voltage will go up, and then you will experience an over voltage condition. So that also you have to consider at the time of optimal planning or placing a renewable sources. So to avoid such situation, or if you want to avoid this very complex mathematics or complex optimal planning problem, generally these renewable sources are distributed in all over the network. That means, for, let's say, now you want to include, let's say, 2 gigawatt of solar plant. So other than just having one plant at 2 gigawatt, you segregate into 20 megawatt 10 plants, and then you just install at 10 different locations. So that will overall increase the system reliability or system condition.
Okay, sir.
Sir, my question is how does smart metering improve distribution system network?
The smart metering actually, it says that first of all, that what I told is demand, like when want to reduce the stress on the distribution grid, first you have to know from which point the stress is coming, because you will see that, let's say some under voltage condition is happening, or let's say some over voltage condition, or network loss is becoming more. So first you have to understand at which point, because let's say you have a 10,000 bus network sitting at the substation, you cannot just point out to a node and say that, okay, this is the main culprit for the the condition. Like, let's say at a node you have 100 customers, you cannot penalize the entire 100 customers. And because those customers are mostly mixed, like some are using very less amount of electrical appliances, some are using very uh, high amount of, like, more electrical appliances, some have 2 ACs, some have 1 ACs, or some have 10 ACs. So depending upon that, the customer criticality level, customer consumption keeps on varying. But as a substation engineer, or let's say power engineer, I am just seeing that, okay, this node is experiencing under voltage condition, so I have to improve that. So if I want to implement a demand response or demand side management, then I will say, if I don't know the loading pattern or the consumption pattern of the customers, each and every customers present at that node, I will tell everyone to do the like take the corrective measures. But let's say as a customer, you are already using very less, and now I am pressurizing you more to use lesser. So that is like a biasness to those customers who are not very flexible. So to avoid those situations, generally the smart meters come, where you will place the smart meter at each and every customer premises. That will give you the visibility of every customer's behavioral pattern and their consumption pattern as well. And that will say that who is the main culprit at that node, who is causing the under voltage. So you will just penalize that customer only, and you just relax the others. Okay, what methods exist to overcome scalability and complexity challenges in distribution system OPF? So generally, to go for like scalability test, or let's say for large networks, generally we use either the distributed OPF techniques, where each and every entire network has been subcategorized or decomposed into multiple small areas, and you just solve for those small areas, and then communication channels will be there to share the data between two neighboring areas. So either we go for the distributed, or if it is not possible to have distributed, then we go for the decentralized, where a large network, let's say the entire city has been divided, let's say for UP. In UP, we have mainly four big distribution networks. One is Purvanchal, one is Dakshinanchal, one is your Awadh, and another is your Paschim. So normally we have 4, 5, and separate dedicated distribution corridor for Kanpur. So we have this 5 different distribution networks, and they run on their own. So they solve their own network OPF. They take measures to incorporate all those control actions, and we don't go for a centralized OPF measures for a very large network. So now generally the decentralized and the distributed algorithms are adopted when your network size goes above, let's say, 500 or 1000 nodes. At that time, it is better to go with the segregation or decomposition method. So any other questions? What are the limitations of traditional OPF methods in modern distribution networks with controllable loads? Okay, so we not said those are like drawbacks or limitations. Actually, whenever this OPF concept only came when your grid edge devices has become controllable. When you don't have controllable devices, because distribution networks previously is a passive, so your loads are not controllable, you don't have generation as well, so there is no point of carrying out OPF analysis, because you know how much power you need. You will take that power directly from the substation. If you don't get that power, you just cut down your loads from your network. So there is no need of doing OPF analysis. We call it a rule-based analysis. That if this much of power is there, then we'll first segregate the most flexible customers if we don't get the entire power. 1 minute. Okay. So that is the rule-based one. So OPF problems only came in the market when your grid edge devices has become controllable, and the loads are more like contributor to that. So before becoming your generation flexible or your generation uncertain because of these renewable energy sources, the loads has become controllable. That now you can control the temperature of the ACs, you can control the operation of your washing machine or clothes dryer or heater, the temperature of your heater or electric water heaters. So actually this OPF concept came for this. So these are not limitation, like there is no traditional OPF kind of thing. This OPF algorithms keeps on changing. The same OPF algorithm which has been solved, let's say 10 years back, with only renewable sources, that has been just evolved with this control loads by introducing new variables, decision variables in that same OPF problem from that controllable loads, considering just to model those controllable loads. How does high penetration of grid forming DG affect voltage profile and reverse power flow in radial and mesh distribution networks? Okay, very nice question. Actually, we have investigated it, and we have seen that generally in grid connected mode, most of the inverters are mostly operate in a grid following, but now as we are increasing more and more renewables, so we are going for the grid forming DGs. So the problems come when your this grid forming DGs are not communicating with each other properly. So if that happens, then at that time, because whenever you are forming your grid forming DGs are coming into the operation, they have their own control algorithms. They have their own set voltages, frequencies, everything. So if they are not communicating with each other, the problem comes because whenever one, let's say one solar panel is generating more power, so obviously the other grid forming DG has to be informed with that, it has to shift from its MPPT point, and then only your system will run in a synchronized manner. But if that is not the case, if that is not gonna happen, then you will have a problem for the radial distribution network. The problem with the mesh distribution network is not much, because you will have an alternative path for you can say channel out those power. But generally that we have seen for solving network, like if you say the OPF analysis or any kind of distribution network analysis, solving the problem with grid forming inverters is difficult, because grid forming inverters will give you more and more variables, and because it has its own control parameters, and that creates the problem. And because of that, generally still for this level of penetration, let's say 30 or 40% level of penetration in the renewable energy sources, still the grid forming inverters are still 5% or 10%. And still, even in the US, utilities are hesitating to change the converter mode from grid following to the grid forming until unless it is absolutely necessary, or until unless it is like very loosely connected with the normal higher grid. So any other questions? Okay. So can we close the session? And thank you for attending this live session and asking very good questions. And I hope you have enjoyed this course, and best of luck for the exam.
Thank you, sir.
Okay.
Thank you so much, sir.
Yeah. So e-learning center, can we just call off the session for the day?
Okay, sir.